Hi everyone, my name is Eyal Golombek and I want to talk to you about work I've done with Benny Applebaum. The name of the paper is called On the Randomness Complexity of Interactive Proofs and Statistical Zero-Knowledge Proofs. Basically, in this work, we try to show how we're able to reduce the amount of randomness required by the verifier in interactive proofs, and we show how we're able to apply those techniques to statistical zero-knowledge proofs. So of course we begin our talk by explaining interactive proofs. I'm sure most of you are fairly familiar with this concept, so we'll go through this very quickly. The settings of interactive proofs, we have some promise problem pi, and we have two entities, the verifier and the prover, where the prover tries to prove to the verifier that some shared instance x is indeed a yes instance. The prover in our settings is computationally unbounded, while the verifier is bounded and runs in polynomial time in n, where n is the length of the shared instance x. We denote with the CV and CP the amount of bits of communication transferred from the verifier to the prover and back, and we denote with K of n the number of rounds that were performed in the interaction. In our settings, it's very important that we also denote the amount of random coins the verifier uses during the interaction, and we denote this number R of n, which is also a function of the length of the shared input. Of course, we will require completeness and soundness for our interactive proofs. Completeness meaning that if X is indeed a yes instance, then the prover succeeds with high probability. And soundness means that if X is a no instance, then every cheating prover will fail in cheating the verifier with high probability. And of course, we're going to talk about zero-knowledge proofs. So a zero-knowledge proof is basically an interactive proof where we also require the existence of some simulator, where the simulator in our settings is an entity that runs in expected polynomial time of the length of the input x. And this simulator, given the input x, if x is indeed a yes instance, the simulator has to output something that is relatively close to the original view of v if v would interact with p on this instance x. So this output of the simulator has to be close, and the way we measure this closeness defines the type of the zero-knowledge proof. So in our setting, we're going to talk about statistical zero-knowledge, meaning that we require that the difference between those two elements will be statistically close. It's important to note that the simulator has, of course, to simulate the interaction between the verifier and the prover, meaning the messages sent from the prover to the verifier. However, it's very important that the simulator is also able to simulate the random coins used by the verifier, denoted here with R. Usually, this is a pretty trivial point. However, in our settings, it's going to be a crucial point in order to show how we're able to simulate a randomness efficient verifier. So our goal is to reduce the amount of randomness used by the verifier in such interactive proofs. And before we can do that, we first want to understand what role the randomness plays before we try to reduce the amount of it. So of course, this issue was studied in the past, and we understand that the randomness has a dual role. First of all, in the soundness, meaning in the soundness of the interactive proof itself. And in the world of secrecy, it has a very important role in preserving the zero-knowledge property of interactive proofs, of zero-knowledge proofs. So in the world of soundness, we know that actually interactive proofs are equal in their computational power to the entirety of p-space. However, we also know that if we reduce the world we talk about to only deterministic verifiers, then deterministic verifier interactive proofs are actually only as strong as NP, which is believed to be weaker than p-space. In the realm of secrecy or zero knowledge, we know that deterministic verifiers, statistical zero knowledge, meaning proofs that are secure against that are zero knowledge and the verifier is deterministic, are known to be only as strong as VPP. However, it is widely believed that statistical zero knowledge is not contained VPP. And so what we understand is that removing the randomness of an interactive proof and statistical zero knowledge proof from the verifier actually reduces the power of this concept, meaning we shouldn't expect to receive a complete de-randomization of statistical zero knowledge in interactive proofs, but what we are trying to aim is the reduction of the amount of randomness used by the verifier, a term that we call randomness sparsification. So let's define the problem a little bit better. We want to create some compiler that, given an interactive proof system PV for some promise problem pi, we want to ask the following questions. First, can we always reduce the randomness required by the verifier? Second, what is the minimum required randomness? And third, can we also preserve zero-knowledge properties under this type of specification? So our goal is to generate some compiler that takes an interactive proof or zero-knowledge proof and generates a new interactive proof or zero-knowledge proof that is more randomness efficient in the terms of the verifier. And so first, let's try and understand what we can expect and what we should aim for. So we know that there are no free lunches, and basically we say that we try to tackle the problem of inefficient sampling, meaning that we try to tackle the problem of taking a computationally efficient entity that is inefficient in the way it samples some distribution. So this concept was discussed in a paper by Dubrov and Ishai in 2006. And basically this means that our verifiers, we try to tackle our verifiers that use more random coins than actually coins that they send to the prover. So of course, information theoretically speaking, it is possible to generate an algorithm that samples in a more efficient, randomness efficient way. However, since the verifier has to be a computationally efficient algorithm, it might not be possible. And indeed, on the other hand, we actually show that in some sense, this is the best that we can hope for, because we show that we can't have a universal way of reducing, using a compiler, of reducing all interactive proofs below the communication, meaning we can't have some pseudo-random generator that universally reduces the amount of bits used by all verifiers below the amount of communication they use. We will formalize this concept in a minute, but just to get a better sense of what we can expect. So in order to achieve our goals, we first define a new construct, what we call an IP-PRG, an interactive proof pseudo-random generator. Basically, an interactive proof pseudo-random generator is an entity that, given some interactive proof PV, and this notation is actually a notation that specifies that the interactive proof runs in k rounds, the verifier uses R random bits, sends CV bits of communication to the prover, runs in TV time, and receives CP bits of communication from the prover back. All of those are actually functions of the length of the input, of course. And we say that G, which extends S bits to R bits, is an IP-PRG if, when taking a look at VG, which is what we call the sparsified verifier, VG is the verifier that takes a short seed of length S, uses G in order to extend this seed to a length R pseudo-random string, and then emulates the original strategy of V using those pseudo-random coins. So if this new VG element, this new verifier, when interacting with P, is actually still a complete and sound interactive proof up to some epsilon reduction increasement of error, then we say that G epsilon folds this specific interactive proof, PV. So it's clear and very intuitive to understand that if such a construct exists, then using it can be a compiler that transforms interactive proofs into a randomness efficient interactive proofs, because we will simply replace our verifier with this new sparsified verifier. Actually, in the paper, we define something that is a little bit stronger than what we defined before, because this element is actually, we define an IP-PRG that is not reliant of the underlying promise problem. If in the previous definition we require that the promise problem, the interactive proof remains sound and complete, here we simply define that this PRG actually makes it that the acceptance probability of V during the interaction for any cheating prover doesn't change even if V runs on pseudo-random coins, meaning that V and VG actually behave the same against any cheating prover, regardless of whether X is indeed a yes instance or a no instance, and the difference between those two terms has to be up to an epsilon. So this really helps us strengthen the definition and actually achieve the proofs in a smoother way. So before we try to show the theorems that in our paper and how we actually show the existence of such an interactive proof PRG, we want to talk briefly about two naive approaches to the problem that actually help us understand the intuition and the motivation behind the definition. So the first intuition and the way we started our search was actually using an entity called a non-Boolean PRG. So let's quickly remind what a non-Boolean PRG is. It is actually an entity that was defined in the paper by Dubrov and Ishai in 06, and it is a natural extension of regular PRGs to the realm of non-Boolean adversaries. So simply put, a non-Boolean PRG is a function G that stretches S bits to N bits, runs in polynomial time, And actually, for any adversary D that compresses those N bits back to C bits, so not just one bit like regular PRGs, but actually C bits, then the output of this adversary is indistinguishable whether it runs on actual uniform random bits or on the output of this PRG. So this is a non-Boolean PRG, and there are very nice, efficient constructions for this element. And so the naive approach is to say, well, we have here a PRG that basically, if you use this PRG and take the pseudo-random output of the PRG and pass it to some computationally efficient algorithm, then the output of this algorithm is statistically indistinguishable than the output of the same algorithm running on actual uniform random bits. So the intuition is to say, let's take this PRG, pass it to our verifier. The verifier would send messages to the prover that are actually indistinguishable of the original message that he would have sent. And so the prover, even though it is an unbounded party, cannot really gain any advantage. And so the prover would have to send messages that are indistinguishable of what he should have sent if the original coins were actually uniform. And so the intuition says that this should preserve the completeness and soundness of the proof. However, what we see in the paper is that this intuition is wrong. And the main issue is that V accept, the predicate that tells V whether it should accept or reject the interaction, actually has access both to the pseudorandom coins, the original pseudorandom string, and to messages that were produced by some unbounded party. And so the naive proof approach doesn't work, and later in the paper we actually show that non-Boolean PRGs are not strong enough to be interactive proof PRGs. So this is one naive approach, and then the intuitive question arises whether we can perform some generic specification in some generic way and try to understand why non-Boolean PRGs actually don't work. And what we know, what we understand is that the reason that non-Boolean PRGs don't work in our settings is that because in our setting we have an unbounded party that is internal to the protocol, meaning it is part of the interaction in our settings. The prover is unbounded, and basically non-Boolean PRGs actually work in the settings where all parties are bounded. For instance, in the paper they show the settings of information theoretical multi-party computation where all parties are actually bounded, they perform the interaction, and only after the fact, only after the interaction is completed, there is some unbounded party that tries to extract more data from the interaction. However, this unbounded party is not part of the interaction. And actually later on in the paper, we show that indeed non-Boolean PRGs are not strong enough to be interactive proof PRGs. And so the concept of maybe having some generic approach to sparsify protocols where the unbounded party is indeed internal and not external. So this approach was studied by a paper by Nuhida and Nanoka in 2012. However, their approach requires exponentially strong PRGs, which are elements that are very hard to generate. And so now that we understand that the generic specification is not going to help us in this setting, we go to our first theorem. We prove the existence of such interactive proof PRGs as we've defined before. And so our first theorem says that for every such functions, TV, CV, CP, and R, we show the existence of a G, a stretching function from S bits to R bits that can be computed in polynomial time. And actually, epsilon fools every non-uniform interactive proof with those parameters for any number of rounds. And the length of the seed of this PRG is actually proportional to the communication plus log 1 over epsilon, where epsilon is the error term that the interactive proof gets added to. So we will soon discuss the non-uniformity, but basically this means that the verifier is a circuit and not a Turing machine. And so if we take epsilon to be 1 over poly error increase, we see that for every promise problem pi with interactive proof with those parameters, we can generate a new interactive proof with S being equal to the communication plus log of 1 over poly, and we get 1 over poly error increase. And so why do we need to tackle only non-uniform interactive proofs and not just interactive proofs? Is because the way we generate our pseudo-random generator is using k-was independent hash functions, and actually our PRGs and hash functions sampled out of a family of hash functions. However, not all hash functions in this family are good, and not all of them are a PRG. And so basically we have to sample such a good function out of the family. So a way to overcome this issue of sampling is actually to hardwire this good hash function for every length n, and this is how we get the non-uniformity by giving the verifier a non-uniform advice of what is this good hash function. We could have told the verifier to simply sample such a hash function out of the family. However, the process of sampling such a hash function would require more random bits than the original randomness of the interaction and would be a very poor randomness specification. And so in order to overcome this issue of non-uniformity, we suggest three solutions. The first one is to use some common random string, where the verifier uses this common randomness in order to sample the good hash function and then perform the interaction with his own random bits and thus overcome the problem of sampling the good hash function. The second solution we suggest is amortization, meaning you can run many iterations in parallel or sequential, many iterations of the problem with the inputs of the same length and simply sample the hash function just once and use it over and over again, spreading the cost of the sampling of the hash function across all iterations. And the third solution that we suggest is actually de-randomizing the hash sampling process, and that's what we're going to see in the next slide. And so indeed, up until now, all of our theorems did not require any hardness assumption or any cryptographic assumption. From now on, for the uniform solution, we will require hardness assumption. Mainly, we will require the existence of some language in d time 2 to O of n that cannot be computed by circuits, by non-deterministic circuits of size 2 to the beta n, where beta is some constant. So this is a very common assumption, hardness assumption. It is known, and actually there are many papers that understand the influence of such an assumption. The main known ones are that actually P is equal to BPP, and the non-deterministic equivalent of this corollary is that NP is equal to A. And so assuming this assumption, we show that actually every promise problem pi that has some constant round interactive proof, pay attention that we are only talking about constant round proofs. So every promise problem with such constant round can have another interactive proof which is randomness efficient, meaning we reduce the amount of randomness that the verifier uses up to the communication plus some logarithmic factor, and we gain 1 over poly increase in the error. So we're actually able to randomness specify every constant round uniform interactive proof if we assume this hardness assumption. So another important point is that actually we show the separation of NP-PRG and IP-PRG. We show that there exists an NP-PRG that is not an IP-PRG, meaning that the definition of non-Boolean PRGs is not strong enough to be interactive proof PRGs. Basically, the way we do it is we define some trait of PRGs called Meliel PRGs. We show that if a PRG has this trait, it cannot be an interactive proof PRGs, and actually we construct a malleable non-Boolean PRG from trapdoor one-way permutation with L incompressible hardcore bits. And this actually tells us that non-Boolean PRGs cannot be interactive proof PRGs, or the definition of non-Boolean PRGs is not strong enough to conclude all interactive proof PRGs. So up until now, we've shown a non-uniform specification of interactive proofs with no hardness assumption, and the uniform specification giving some hardness assumption. Now we will try to apply those techniques to statistical zero-knowledge proofs. First, we understand that if we tackle statistical zero-knowledge proofs that are secure against malicious verifiers, we know that this is a trait of the prover and not of the verifier, and simply the techniques we've developed, both the uniform and the non-uniform, actually trivially expand to those proofs, since a sparsified verifier can be treated as simply a malicious verifier, and the new sparsified proof is still secure against this verifier. However, we show in a paper that there is a special interest in talking about honest verified statistical zero-knowledge proofs. Even though we know that honest verified statistical zero-knowledge proofs is actually equal to SZK in terms of computational power, we see that all transformations, both classical and more modern transformations, actually, if there was a gap between the randomness and the communication, those techniques close the gap in a way that is not randomness efficient, meaning those transformations actually raise up the communication with the verifier up to the random coins that it uses. And so those transformations do not help in randomness classification. And we understand that the paradigm we want to tackle is actually first sparsify honest verifier proofs and only then transform them to statistical to proofs that are secure against malicious verifiers. And this way we gain the randomness classification. And so we tackle the problem of sparsifying proofs that are secure against honest verifiers, statistical zero knowledge. And so let's first gain some intuition of how the simulation would work and why it is not straightforward. And so we have here a sketch of our verifier interacting with our prover, and recall that our verifier actually samples some short seed random string and uses the pseudo-random generator in order to expand the string into a much larger pseudo-random string. Pay attention that the image of the pseudo-random generator is actually very sparse in all of the possible random coins to the verifier. And so one issue, if we simply try to use the original simulator in a black box way, is that this original simulator will generate some output that is relatively close to the interaction of the original verifier and the prover. However, the simulated random coins, the chance that they will fall inside the image of G is very small because the image of G is very sparse. And so it is highly unlikely to eat the image of G. Moreover, even if the simulator actually generates simulated coins that are have a pre-image under G, it is not very understandable how we should generate this seed and how we should invert the PRG to simulate also the seed, which is part of the view of the sparsified verifier. And so actually what we do in order to overcome those issues is that we understand we can define a new construct of statistical zero knowledge. We define zero knowledge proofs that are secure against semi-malicious verifiers. And what is a semi-malicious verifier? A semi-malicious verifier is actually a verifier which runs the honest verifier strategy, but samples the random coins in some malicious way. And we define a semi-malicious verifier with some constant f, which is a number between 0 and r, which denotes the amount of bits that the semi-malicious verifier actually samples in a malicious way. Simply speaking, the semi-malicious verifier uses some distribution D, it is efficiently computable, in order to sample f bits, and then expands those f bits into an r long string by using completely uniform and random bits, and then passes this new random string, pseudo-random string, to the honest strategy and performs the interaction with the prover. So basically, we understand that swapping the distribution is not completely malicious. However, it is not really an honest verifier. And here you can see the formal definition. We will not go into all the details, but basically, this means an interactive proof is secure against semi-malicious verifiers if for every distribution, for every efficient distribution that outputs f bits, this interaction between the semi-malicious verifier that uses D as the random coins, this interaction can actually be simulated by some simulator SimD, which is dependent of this distribution, up to some error factor, which is the simulation deviation. And so what we see is that using this new construct, we're able to generate interesting trade-offs between the randomness of the verifier and some other components of the interaction. For instance, we show a trade-off between the verifier's randomness and the prover's communication. We show that if you have some interactive proof that is secure against F semi-malicious statistical verifiers, then we can create a new interactive proof for the same promise problem that is secure against honest verifier statistical zero knowledge at the cost of adding one more round, which is simply the prover sending random bits to the verifier, and the amount of bits that is required to be sent is actually R minus F. And we see that this F plays a key role in the trade-off. And actually, if we get an interactive proof that is secure against R semi-malicious verifier, meaning that F is equal to all of R, then this term cancels out and we get simply an interactive proof without any additional communication from the prover. Another interesting trade-off that we show is a trade-off between the randomness of the verifier and the simulation complexity, the amount of time the simulator runs. The first trade-off we show doesn't include semi-malicious verifier. It simply shows that if we have some interactive proof that is secure against honest verifier or perfect zero knowledge, we can transform it into a new proof that is randomness efficient, and the simulator runs in time poly times 2 to the power of r minus s, which is indeed not polynomial, but we gain some trade-off. And another interesting trade-off that we see is that if the original proof is actually secure against F, semi-malicious perfect zero knowledge, then we can transform this interactive proof into a new proof where the simulation, which is randomness efficient, and the simulator runs in expected time of poly times 2 to the power of r minus f. And basically this means that if the original proof had f equal to r, then there is no cost in the simulation complexity, and we gain just a plain simple randomness sparsification. And the last interesting point is that actually we show that this is indeed a meaningful relaxation between honest verifier and completely proofs that are completely secure against malicious verifiers, because if we take R all the way down to 0, we get honest verifier statistical zero knowledge proofs. But on the other hand, we show that statistical distance, the classical canonical interactive proof for statistical zero knowledge, is indeed secure against R semi-malicious verifiers, and we know that the original interactive proof is not secure against malicious verifiers. And so we get some interesting concept between honest verifier and proofs that are secure against completely malicious verifiers. Thank you.